So we will hear a presentation from Tariq Mohammed, who works for Kite Mill and is also doing a PhD with Professor Lorenzo Fagiano at Pomini. Please go ahead.
Okay, so it's my pleasure today to give a talk about fault-tolerant control, fault-tolerant aircraft control in traction phase of public airborne wind energy system. So the system we are considering here is a rigid kite or rigid glider, and as you see here, we need to control the kite in traction phase about some imaginary plane, this one, and we try to fly in circular path in that plane. So this is in this particular phase of flight, we want to apply active fault-tolerant control. I will present some videos. So this is the 20 kilowatt prototype from Kite Mill, test site at Testa, Norway. So this is the takeoff, and yes, we just reel out until we reach predefined altitude. Then we reel in the tether in order to accelerate the kite and do the winch launch, as you see now. And yes, when we gain some speed, we disengage the VTOL system and we start crosswind flying, as you see. So the question here, what if discrete surface failure happens? Are the VTOL system able to continue looping? This is the question we try to answer with this research. So what we did is that we tried to build a model. So it's like this. The problem is that we can inject some failure, but will be more costly if the failure ends with a crash. So we try to build a simulator. Maybe this is not the main purpose of the story, but it was needed. So I will go to this slide here. So we considered the models developed by Sebastian Rapp. The aerodynamic data, he has some aerodynamic data from safety analysis. This prototype is Kite Mill KM0, 5 kilowatt. Wing, yes, the mass is 4 kilogram, and the wing span is 3.7 meter. So in order to validate and verify the simulator, we take some experimental data. We find the path during looping, and we try to tune the controller in the simulator in order to follow the same trajectory. And when we get the same, like not the same, but yes, more close path, we try to collect the data. We take two main data or two main metrics: the airspeed of the kite and the tether load, the tether tension. As you see here in the histogram here, the first figure showing the load on the kite, on the tether, and what we get from the simulator. So in the simulator, we get like from 400 Newton up to 900 Newton with two peaks in like 500 and 900. And in the experimental, we get quite similar histogram. So we consider that this is a good match. The second thing we compare to validate or to verify the simulator is to see the histogram of the air kite airspeed. So in the experimental also we have two peaks, one about 33 meters per second, the other one is around 40 meters per second, and the simulator in the orange it is, yes, the same peaks and maybe, yes, have good match. So we consider that now we have a valid simulator to test our control. And so this is, yes, it is not only about modeling the aerodynamic characteristics of the kite, it is also about building good tether model. So this is the tether model which consider the aerodynamic effect and the mass, and we also validated through some simulation. Then what we did is that we also tried to build a good model for the quadrotor. So the quadrotor is the thrust is also affected by the apparent airspeed of the kite, since we are flying very high speed. So we built some solver to build some table that match the RPM of the VTOL system of the rotor in different relative airspeed, and then we include this all data from the simulator. So we have the simulator for the VTOL system, for the tether, and for the kite itself, or the glider itself. Then we build a dynamic control effectiveness matrix. This dynamic control effectiveness matrix can translate the surface deflection to the moment of the discrete surfaces, denoted by MS. The thing about this dynamic control effectiveness matrix is that we will use it online. We have sensor for the airspeed, for alpha, beta, and we will compute it online to get benefit from it. Similarly, we build also dynamic control effectiveness matrix for the quadrotor system. And this dynamic control effectiveness matrix, denoted by BQ, will be used to transfer between the RPM of the VTOL system and the thrust and the moment of the quadrotor. And here is the suggested control architecture for active fault tolerance control. So we assume that we have a low-level controller during looping, and this low-level controller will give some control surface deflection. We will not discuss it now, but here we have this control surface deflection, delta A for the aileron, E for the elevator, and delta R for the rudder. And the controller will convert, because you know that we calculate the BS online, we can convert it to the moment from the discrete surface, MS. Since the low-level controller is built based on a linear based controller, and it is not taking into account the tether effect and other disturbance, we also find it is more useful to include internal model control here. And when we get the output from the internal model control and we add it to the moment coming from the discrete surface, we obtain the desired moment. So this is the desired moment to keep the kite looping, flying. And this desired moment could be produced either from the quadrotor or from the discrete surfaces. In normal scenarios, we will compare this desired moment to control surface deflection and feed it directly to the kite. But at the same time, we will using BQ and control allocation and saturation management algorithm, we also compute what is the required RPM from the VTOL system to produce the same MD. But this we will not use it in normal situation. Here we have a fault detection and isolation algorithm. We only compute the residuals about Rx, about longitudinal axis. We also compute the residual about yawing axis, as seen in Rx and Rz. And if any of these residual cross some predefined threshold, we will isolate the surfaces completely, and we will use the quadrotor to take control, as you see here. And because when we inject, when we use the VTOL system, the residual will decrease again, and then that's why we are using here threshold lock. So this is the control that we suggested. So we have tested this controller in two scenarios, two extreme scenarios. When the kite is going up in stroke, and when the kite is going down in looping. Here I will present the result of when the kite is going up, because it will go against the gravity, and it is most extreme case. So we're looping for, the simulation is like this. We're looping for like 80 seconds. Everything is normal. This is the rudder deflection. And at the second 70, we injected a failure to the rudder. The rudder is the most used discrete surface in loop. So we injected the failure to the rudder at the second 17. In normal operation, the rudder will act like this, in the green line. But the failure mode is just we fix it at 0. Here you see that the moment produced by the VTOL system. So after maybe 3 seconds, the fault detection and the isolation algorithm will disengage the control surfaces, and we'll use the VTOL system instead. And you can see that we start to produce some moment by the VTOL system. This is the residual which we use to detect the failure. Here we have the residual from the tethered axis. At the second 17, the residual starts to increase. And in the black line, when we engage the active fault-tolerant control, it decreases again. That's why it's important to use a threshold lock. Also, we found that RZ is also able to capture the failure. You see here, the residual starts to increase. And then yes, we just, when we engage the active fault-tolerant control in the black line, decrease again. But in this dashed line, we are not applying any fault-tolerant control, and the residual start to increase. So this is the trajectories of the simulation. As you see here, this is in the right, when we don't, the gray line is the normal flight trajectory without injecting any failure. But the black line here, the failure is injected somewhere in the loop. And when we don't have any active fault-tolerant control, the kite go out from the loop, and maybe we have a failure in the system. And you can see here the altitude in the dashed gray line start to decrease and loop and then go down. But here, when we apply active fault-tolerant control, the VTOL system is able to kind of follow the same trajectory as normal flight. So as a conclusion, we propose active fault-tolerant scheme to react instantly in case of discrete surface failure for hybrid fixed wing quadrotor Airborne Wind Energy System. And the suggested controller has been tested in verified simulator and shows that the quadrotor is able to provide redundancy to discrete surfaces for flight control. Thank you.
One or maximum 2 questions.
Yes, thank you very much. What would happen if it wouldn't lock at a 0 position, the rudder, but say it would lock at some fixed position, would go completely slack, say because of an actuator failure? Would the same methodology still be able to recover that?
So we didn't test that, but it will be like this. If the VTOL system is able to provide, because we have internal model control, if the quadrotor is able to provide high amount of moment to counteract the failure, it will do, because we have the internal model control and it's very robust. That's what I expect.
thank you again.